some fundamentals of electrical engineering. In control system, we have progressed a little, though we were still on time response analysis. We had moved through the transfer function understanding, the steady state error, and one session in time response. Now let's go to the next session in time response. So what do we have here? We have the first problem, something similar to what was discussed in the earlier session. The closed loop transfer function of a control system is given by Cs by Rs 2 into S minus 1 divided by S plus 2 into S plus 1 for a unit step input. The output is what? Now we of course have a brief glance at the different options given, and it's obvious that Rs is going to be equal to 1 by S. So now we are going to have three quantities on the denominator of Cs. One is 1s, another is S plus 2, the third is S minus S plus 1. So we are going to have e raised to minus 2t, e raised to minus t as two terms, and of course we'll also have some constant, okay, or ut into some constant, okay. So now, so hence options A and B are acceptable. One of them is more true. C and D are rejected immediately. So now we move on to so we see that e raised to minus 2t we have, again the coefficients are the same, minus 3. E raised to minus t we have two different coefficients, one is 4, the other is minus 4, and then the constant. The constant is given by the term of k by s. So let's estimate k as the residue of s, okay, or residue associated with 1 by s, okay. So for that, this is much easier, that's why I'm doing that, okay. So now we have 1 by s into 2 into s minus 1, s plus 2 into s plus 1 to obtain the residue multiplied by s, okay. So the s and s cancel, and then substitute for s as equal to 0, okay. So on the numerator you have minus 2, on the denominator you are going to have 2 into 1, 2. So the residue is going to be minus 1. So the constant is going to be minus 1, and that appears in A. On the other hand, if you want to find out the constant associated with S plus 1, which gives you k into e raised to minus t, whether it is 4 or minus 4, the only thing that you've got to do is to multiply 2 into s minus 1 by s into s plus 2 into s plus 1 by s plus 1. So s plus 1 disappears, and then put s equal to minus 1. You see that it's the same as equal to plus 4, because you're going to have minus 4 on the numerator and the minus 1 in the denominator. As simple as that, okay. So we need not take out all the residues or something like that. So make a large number of guesses. That's all, okay. So let's go to the next problem, wherein Rs is given. There's a unity feedback system, negative of course. K is a magnifier, and then we have VAS, which on passing through the block 10 by 1 plus 10s gives us the output as equal to omega s. Looks like a tachometer or something like that. The open loop transfer function of a DC motor, okay, of course, is given as omega s by VAS is equal to 10 by 1 plus 10s. Okay. When connected in feedback, as shown below, the approximate value of k that will reduce the time constant of the closed loop system by 100 times as compared to the open loop system. That's a very good application for reducing the time constant by 100 times. Okay, so immediate response is possible. Okay, so first we calculate the open loop transfer constant open loop time constant from e raised to minus 0.1 t. By e raised to minus 0.1 t, 10 is taken out, so 10 and 10 cancel. So now we have 1 by 1 plus 1 by s plus 1 by 10. So e raised to minus, or 1 s plus 0.1. So e raised to minus 0.1 t happens to be the quantity that we are considering. Of course, with the multiplication of k, but the time constant appears as the reciprocal of the coefficient of t here. So it's going to be 1 by, of course, with the time constant, because it is minus, it means that it's a decaying thing. Okay, so we are having 10 as the time constant. Okay, so for the closed loop system, now we are going to have Ka into 1 by 1 plus, so S plus 0.1. Okay, so now we are having two quantities there, s plus 0.1. Okay, so when you are taking the closed loop system, again it becomes the same as equal to the Ka also gets added because it's going to be Ka. The open loop transfer function now is Ka divided by s plus 0.1. So the closed loop transfer function becomes the same as equal to Ka divided by s plus 0.1 plus Ka. So now we have the fact that and hence the exponential is now going to be e raised to minus 0.1 plus Ka t, and so the time constant is going to be the reciprocal of 0.1 plus Ka, and this has to be this has to be 100 times. Okay, so the closed loop system has to be 1 by 100th of whatever was available for the open loop system. So 10 divided by 100 is equal to 0.1. So you equate 1 by 0.1 plus Ka is equal to 0.1. So now we have we have Ka plus 0.1 is equal to 10, or Ka is equal to 10 minus 0.1 or 9.9. Okay, so amongst the different answers given, we see that C is very near, or is the only one which is very near to 9.9. So that's equal to 10. Okay, so moving to the third problem, the response ST of a linear time system to an impulse delta t under initial relaxed condition is St is equal to e raised to minus t plus e raised to minus 2t. The response of the system for a unit step input, as we had done earlier, you take the integral. Okay, so you have one of the terms would be e raised to minus t into minus 1, then the other would be minus 2 into e raised to minus 2t. Sorry, it would be e raised to minus 2t by minus 2t minus 2, that's equal to minus 0.5 e raised to minus 2t. So we have two terms there emerging in option C, and then for t equal to 0, you see you know that at t equal to 0, the input, there is initial relaxed system, so the output will be equal to 0. So you need to have a constant which will negate out minus 1, minus 0.5 or minus 1.5 at t equal to 0. So we have 1.5 minus e raised to minus t minus 0.5 e raised to minus 2t as the, starting at ut, as the response of this system to a unit step input at t equal to 0. Okay, so let's go to the next problem, the fourth one. It is an open loop control system, results in response of e raised to minus 2t sine phi t. Okay, so there are two damped sinusoids. One is e raised to minus 2t sine phi t, and the other is e raised to minus 2t cos phi t. Unit impulse input. Okay, the DC gain of the system. This is different. To get the DC gain of the system, you have to set S is equal to 0 in the Laplace transform of e raised to minus 2t sine phi t plus e raised to minus 2t cos phi t. So what's the Laplace transform? It's the same as equal to omega divided by s plus alpha whole square plus phi square for the sine component. For the cosine component, it's going to be s plus alpha divided by s plus alpha whole square plus omega square. Okay, so that's given there, where alpha is equal to 2 and omega is equal to 5. Okay, so once that is done, you see that you are having, and then when you set s is equal to 0, it's going to be 5 by 10 5 plus 4, 29 plus 2 by 29 or 7 by 29. Okay, 7 by 29 is more or less near to 7 by 28 or 1 by 4. So from amongst the answers, you can of course calculate thoroughly, rigorously, but then the answer B is the nearest that is possible to the answer, and you know that's correct. Okay? Moving to the fifth problem. A two-loop position control system is shown below. So what do we have? In the first loop, we are having Ks as a taper generator, and we also, of course, taper generator because it's proportional to speed. Second is, of course, the unity feedback. Okay, both are negative in nature. Okay, so from the first loop, you obtain 1 by s square plus 1 plus Ks. Okay, and then from the unity feedback loop, you get, we already had 1, so 1 remains there, and then you have what is called as s square plus s square plus k plus 1 s plus 1. Okay, because numerator never had anything other than 1. Okay, so plus 1. Okay, so that's the closed loop transfer function. The two loop position control system is shown below. the gain k of the Taco generator influences mainly the, okay, so what is gain k? Gain k comes as the coefficient of s, okay, with along with k, as k plus 1, okay, along with 1. So now that has and k plus 1 is going to be equal to 2 eta omega n, okay. So omega n does not influence anything here because k is mostly okay, omega n is 1, so in eta is definitely k plus 1 by 2. Okay, so now this influences what is called as the peak overshoot, because peak overshoot is given by purely e raised to minus pi eta divided by square root of 1 minus eta square. So now it influences the peak overshoot, and that's the first answer, so we don't go further. Moving on to the sixth problem. A unity feedback system has an open loop transfer function Gs is equal to 25 divided by s plus 6. The peak overshoot and the step input response of the system is approximately equal. So it's a unity feedback system. So the overall transfer function is given by 25 divided by s square plus 6s plus 25. Okay, and then so we have omega n is equal to 5, eta is equal to 6 divided by 2 into 5 or 0.6. Okay, so now we can calculate the peak overshoot as equal to e raised to minus pi into eta, where eta is equal to 0.6 divided by square root of 1 minus 0.6 square or 0.36. Okay, so 1 minus 0.36 is immediately 0.64, and the square root is going to be 0.8. Okay, so 0.6 by 0.8 gives you 3 by 4. So e raised to minus pi into 0.75. Very simply, you can calculate that. If you can see that it's equal to 10%. The next problem is also similar, because we are given an RLC circuit with R is equal to 10 ohm, L is equal to 1 millihenry, and C is equal to 10 microfarad. Okay? So omega can be calculated. Okay? For a step input EI, the overshoot in the output E0 will be what? Okay? So first and foremost, we calculate EOS by EIS, because EO is what is asked. Okay? And the step input is 1 by s. Okay, so we have EOS by EIS by what is the output? That's across the capacitor, so 1 by CS. So 1 by CS is the same as equal to 1 by 10 into 10 raised to minus 6s or 10 raised to 5 by s. On the denominator, you are going to have R plus SL plus 1 by CS. So R is 10, SL is 10 raised to minus 3 into s, and CS, as we saw, 1 by CS is the same as equal to 10 raised to 5 by s. So now expanding it appropriately, taking out 10 raised to minus 3, etc., and taking x downward or to the denominator, we see that the result is going to be 10 raised to 8 because of 10 raised to minus 3 there. And then you are going to have s squared on the inductor, which is going to be multiplied by s, and 10 raised to minus 3 has been taken out. The resistor becomes purely 10 raised to 4s, 10 and into 10 raised to 3, and then s. And now we have the capacitance replaced by the compound component associated with the capacitor is replaced by 10 raised to 8. Okay, so 10 raised to 8 and 10 raised to 8 on both on the numerator and the denominator, the constants tell us that omega is equal to 10 raised to 4. Okay, it also tells us that eta is going to be equal to 10 raised to 4 divided by 10 raised to 4 and 2. So eta is equal to 0.5. So very simply, you can see that the maximum peak as MP is the same is equal to e raised to minus pi, eta is 0.5 divided by square root of 1 minus 0.5 square, that is equal to 0.25. So that's 0.75. When you take the square root, 0.5 comes out again, and so you are going to have but there's a 0.5 on the numerator, so minus pi divided by square root of 3. Okay, square root of 3 is near around 1.732, and the pi is 3.14, near around e raised to minus so e raised to minus 2. So if you even substitute, if you know that E is near around 1 by E is near around 2.7, so 1 by 2.7 square or something like that. So you can, it's easy to see that you have something like 16% as the without even using your calculator, you can calculate that. Okay, moving to the last slide and the 8th problem. The unit impulse response for second order underdamped system starting from rest is given by CT is equal to 10.5 e raised to minus 60 sin 80. So CS is very easy to calculate as equal to 12.5 is there into this sign. So omega, that is 8 divided by s plus 6 into whole square plus 8 square, because 8 omega is 8 and alpha is equal to 6. Okay. And what is asked is the steady state value of the unit step response of the system. So again, there's going to be a 1 by S, and then you've got to find out the steady state value. So what do? Multiply by S, and so that S cancels. Then then you go for S is equal to 0. Okay, taking the limit, the final value here. Okay, so we have 6 square plus 8 square on the denominator, which is equal to 100. Then you are having 12.5 into 8, which is also 100. So 100 by 100 is equal to 1. Very easy. Okay, so yeah, just as the last problem, where a control system with certain excitation is governed by the following mathematical equation. So what's the mathematical equation? D square x by dt square plus half dx by dt plus 1 by 18x. Okay, so now we've got to convert it into Laplace transform, and we have also got to take the factors there, such that on the numerator, on the left hand or the right hand side, you can see 10 plus 5 e raised to minus 40 plus 2 into e raised to minus 40. Natural time constant of the system of the response of the system are asked. Okay? So natural time constant will always be given by whatever is going to be the denominator, and the denominator comes from the left hand side. Okay, whatever. Let's write out the characteristic equation as equal to. Okay, characteristic equation is given by the system and not by the input. Okay, input is 10 plus 5 e raised to minus 40 plus 2 into e raised to minus 5t, about which we don't bother, but we take the Laplace transform of the left hand side. We are left with s square plus 1 by 2 s plus 1 by 18. Okay, so please be very clear about it. When you're talking about natural constants, time constants, etc., it is about the system only. So now s square plus 1 by 2 s plus 1 by 18 can be easily factorized as s plus 1 by 3 into s plus 1 by 6. So you have two poles, 1 by 3 and 1 by 6. Okay, and so since s is in omega, and that is dimensionally compatible with 1 by time. So and then you are having such a relationship, it means that it is not 1 by 3, which is the time constant, which is going to be 3. Okay, so 3 and 6 happen to be time constants. Okay, so all these things you can do immediately and obtain the understanding. So this is something that that is a part of a concept, in the sense that only the system is what has time constants. Okay, so that's why we take the Laplace transform of only d square x by dt square plus half dx by dt plus 1 by 18. Okay. Second concept happens to be that you can you have the characteristic equation, and the characteristic equation is going to give you the time constants. Okay, but in what nature? As reciprocals of whatever are going to be the poles. Okay, why? Because poles are going to be would be expressed in the frequency domain. So so time domain will be reciprocals of that. Okay, we also saw that we have two quantities describing any kind of damped functions. One is going to be alpha, which is going to be the when it's damped, it's going to be e raised to minus alpha t. Okay, and of course it's oscillatory, so we have sin omega t and cos omega t. Okay, we also saw that we saw e raised to minus pi eta divided by square root of 1 minus eta square. It can be very much easily simplified by even approximate value, so long as you know the value of e as also 1 by e. Okay, and also 1 by e square. Okay. So yeah, so we saw that, and we saw that it's always going to be the peak overshoot is always going to be affected by eta. Okay, of course, because peak overshoot is given by e raised to minus pi eta divided by square root of 1 minus eta square, and eta only, and eta happens to be the coefficient of the s. Okay, in a second order description of the characteristic equation as given by s square plus 2 eta omega ns plus omega n square. Okay, we also saw that in a motor you can reduce the time constant by going for a closed loop transfer function, or going for feedback, which even to 100 times by having a magnifier or an amplifier of magnitude Ka there. Okay, so once you do that, if you reduce the time constant, the speed of the response increases. Okay, and we checked out two different problems wherein the integral of the that the output can be obtained from in the integral of the of the response of a system to an impulse. Okay, so in all these aspects, we must also remember what happens at t equal to 0, as also sometimes the slope of the system. Okay, so by this with this session and with this slide, we complete the time response in the time analysis of control systems. Okay, so first it was transfer function, thereafter it was a steady state analysis, steady state error, and now we have looked at the time domain function as such, both from its origin to its steady state value. Okay, I suppose we are now ready for taking on the block diagram and the signal flow graphs in the next session.